Hi class, good day to you. And again, welcome to the continuation on the lectures on electrodynamics. And I'd like to again mention our main reference, Introduction to Electrodynamics by David J. Griffiths. And this book is recommended for you. Uh, you can buy this. You can buy this online. So anyway, I'm trying this new way of doing our lecture. um, I hope we'll be able to get the feel of that as we do this session. So we started out with calculating electric fields, and wait for a moment. I'm just adjusting something. So okay, so we were calculating electric fields, but this time in this session we'll be doing calculations of electric potential, which are much easier to manage and gives us the same answers as we um, derived in the previous lectures. So we begin with Poisson's equation, and then we'll have a special case called Laplace's equation. The electric field, as you have known, the electric field is actually a negative gradient of a scalar potential here. So it's a gradient of a scalar potential. And when you go and simplify the equations that we have derived before, like for the electric field here, it's this is given by this one is the differential form of the Gauss law. And so if you replace this one with negative of the gradient of the electric potential or the scalar potential, you will be able to get this equation. And by the way, of course, the curl of E is always 0, because the gradient of V, as we've studied in chapter 1, the curl of any gradient is 0. That's given by this one. And by the way, this oh wait, I got lost. Wait, so let's go back. So anyway, this one right here is called the Laplacian of V. That's the second order three-dimensional derivative of the electric potential. So that's it. So this one is called the Poisson's equation here. Poisson's equation. So when you are in a region that charges are not present, so in that case, the charge distribution would be uh, zero anywhere, so that you will have this. The Poisson's equation reduces to a Laplace's equation, and that Laplace's equation would just be this one here, that one. And of course, yeah, I talked about this a while ago, that the curl of a gradient is always zero. So let's look at this scenario, the potential of a localized charge distribution. When you say localized, it's like that system is isolated from anything. The universe will not affect that um, system. Localized. So before we calculated electric field, but now it could be much simpler to start with calculating the electric potential first. So if we know the charge distribution, if we know that there's a presence of charge somewhere, then I think we can calculate V without the mess that the directions of the fields are putting us in the integration of the electric field. So in this case, you're just going to calculate the electric potential. So if we have a point charge at the origin, so if we have a point charge at the origin, and we set, of course, when you calculate the electric potential, you set the reference point at infinity, and at that point, or at infinity, the potential or the value of electric field or the potential is zero. So in this case, you have here this expression here. So again, from this this equation actually came from when we look at this one right here, where this is our basis of the potential. So the electric field of a charge is given by this one, and then you put the E inside here, but the dl, as we have discussed in the previous lecture, the dl would just be dr r hat plus r sine theta d theta hat plus r squared sine theta d phi hat d phi hat. So the dl would just be the contributing dl would just be that component with the direction r, because this is that you're operating a dot of a vector to another vector. So E is in the radial direction, so the dl that contributes with that is just the dr direction. So so here your V is actually this one. So So anyway, that's recalculated here. For a potential of a point charge at the origin. So I think I have to take off my video, my I mean this circle here, that I'll just get back to that later. So this one here, you have the expression for the electric potential, and if you have so many distribution, you were just considering this one, we were just considering this one right here. But if we have many charges in the region, then we can impose the superposition principle, this one, superposition principle. By the way, here you notice that V is equal to that, and actually if you have a charge that is very small, say for example dq, so your electric potential given by the dq is just dv equal to 1 over 4 pi epsilon sub o dq over r. So that's just that's the derivative of v, and then on the other side you get the derivative of q. 1 over 4 pi epsilon would just be a constant, so, and of course the one giving you the electric potential is dq, so that's the derivative of v. R, as I've told you, the R, the script R is the distance from the charge q to the point P where you are measuring the electric potential. So it's the point P here. So this is the R that I'm talking about, this one and that one. Of course, in figure 2.32 you can see one charge on the first, and on the second you have several charges. On the third you have a distribution of charge, a continuous distribution of charge. So now, so when you have so many charges, just like what's in this here in this figure, to calculate the potential there, you consider all the electric potential given by all the individual charges. So you get to the sum of the potential, the electric potential. That's that. And for continuous distribution, the summation here, the summation will just convert to an integral. You know that you know how to operate the integral already, and we will not be discussing that, of course, the nitty-gritty of integration. And then your qi will become dq, and of course the ri here will just be r. So let me just erase everything. So in by the way, in particular, if you have a solid distribution of charges, then you can actually, as in the previous lecture, dq is just equal to rho d tau, derivative of the volume, because for a uniform distribution, of course, rho is equal to q over the total volume tau. But if you have a distribution that is not constant or not regular, or in general, you can write this as dq over d tau, so that your dq here, so that our dq here will be replaced with rho d tau. Now we go further. I'll just read the caption of that equation. These equations give how to compute when P is known. It is a solution to Poisson's equation for a localized charge distribution. So if you look at, if you go back to the electric field, if you compare the electric potential and the electric field expression, you will see that you have this factor here. This factor, of course, you have the integral, you have the rho, you have d tau and d tau here. And then the thing that we notice is that there's no more direction in equation 2.29, unlike here in this equation. So by the way, this is for volume. This equation is for volume distribution, but if you have a distribution of charges on a surface, or you are dealing with a line charge distribution, then the potential would be calculated by these two. So you just change dq with lambda dl and then sigma dA. So by the way, there's a warning here. It is assumed that the reference point is at infinity and the value there is 0. So if the formulas are applied to charges that are distributed on an infinite design, or infinite surface, for example, or volume, or infinite line, then you will not be able to get the integral of that, because the potential at infinity will not be 0. So you have to find another reference point in which the potential has to be 0. So anyway, we discussed that in the previous lecture. Now we'll deal with example 2.7. So here we're going to find the potential of a uniformly charged spherical shell of radius r. So we talked about this in example 2.6, but this time it will be done by using this. So in this case, you're talking about a spherical shell. So a spherical shell doesn't is like a surface charge density you have there. So we'll be just using this. We'll be using this formula to find the electric potential. So here, if you have if you look at this figure, you have a patch of area right here. You have a patch of area here. That's the surface area of the spherical shell. And so you are going to find the potential find the potential either inside this shell or outside the shell. So here by the way, the R here, if you are inside the shell, if you are inside the shell, by the way, Z, if you're inside, Z would be less than R. So because the P would be now inside the sphere, but this is inside, and Z is greater than R outside. Okay, so we'll continue with the problem. There's a triangle that is formed here, by the way. So here we take a look at the triangle. The radius of the sphere is R. This is the radius of the sphere, and the patch of area is always located at the surface of the sphere. So it's always a distance R from the origin, distance big R from the origin. Your point, the P, can be located outside or it can be located inside. So whichever is the point P located, that would be dealt with later. So we'll just look at this situation here where P is located outside, or it's located on the z-axis, for example. So there's a measured distance from P with the origin, and this is Z. Yeah, it's there, Z. And of course there's the distance between the DQ here. This is DQ. This is a DQ. The DQ has a distance R to the point P. That's what it means in the equation, in our expression for the electric potential. And of course it's also the same as in the electric field. So let's do it here. So you have the sigma is, you can take that out because sigma is uniformly charged spherical shell. That means the sigma is constant. So you can take that out of the integral. The sigma can be taken out of the integral. You can take this out here. So you have and this one, if you can see this constant is just multiplied to that, so that you have a simplified expression on the right side. So your 4 pi epsilon is multiplied to electric potential here. It's just a cross multiplication, and so your sigma comes out of the integral, and the dA, of course, if we recall the problem in 2.6, which you have, I think you have already studied by now, the dA would just be the component that is the radial component of the dA, the directional area, because we are dealing with the patch of area here on the surface of the sphere. So anyway, you can review 2.6 and you can get r squared sine theta squared d theta r squared sine theta prime d theta prime d phi prime. And the r here is, of course, the cosine law. The cosine law of this is the r here is, this is a triangle, so you can find the length by cosine law. Of course, Pythagorean theorem is a special case of the cosine law, but this is not Pythagorean theorem because you don't have a right angle here. So in general, you don't have a right angle, so you have here this expression now, and of course, if you integrate d phi, that will just be from 0 to 2 pi. So 0 to 2, if you integrate d phi prime, that would be phi prime evaluated from 0 to 2 pi, so your 2 pi comes out here, and then your r squared will come out also of the integral, and you're now going to integrate with respect to theta here. So sine, theta prime, sine theta prime d theta prime, and your expression in the denominator is a function of theta prime also. So if you let the expression below equal to some variable, so that you can write it in terms of that variable, and then you can integrate easily, or you can use some formula of integration. So you will have this expression if you have integrated that, and then here you will have simplified expression over here if you have evaluated from 0 to pi. Then you should be very careful in this one is r plus z square. This one here, this one is r plus z square, and this one is r minus z square. And if the point is outside, z would be greater than r, and if the point is inside, z would be less than r. So you have to be very careful in getting the square root of this and this one, because it may not be valid because of the negativity of the argument inside the square root. So here you have so for points outside the sphere, you have z greater than r, and then you have this one, and then also for points inside the sphere, you have that one also. So anyway, for the potential inside the square roots become this. Okay, this is for outside the sphere, and this one, the other one is for inside the sphere. This one is for outside the sphere. Be careful with getting the square root. So that's it for the example. So we now proceed. You can also try this problem at your convenient time. Problem 2.25. You also have other problems here, 2.26, 2.27. I'll not be reading these to save time. 2.29. And now let's go to the electrostatic boundary conditions, because all the problems, just like our reference point in calculating the electric field and calculating the electric potential, we needed the reference point. That's one of the boundary conditions. There are also other boundary conditions that we're going to discuss. These are the electrostatic boundary conditions. So let me just read. Of course, in a charge distribution, ρ, that distribution will actually give you the electric field and also the electric potential. And what's good with the electric potential is that, or the potential, or should I say just the potential instead of electric potential, that means the same. Potential has no direction, while electric field has direction. So it's much easier to calculate the potential than the electric field. So again, we saw that the principle of superposition is applied to the electric field as well as the electric potential. And of course, the Coulomb's law, we can, if we could remember the first lecture, that's just the quantized, or the quantity of force that's acting between two charges. So here we have a diagram. So you have um, a potential here that's that's calculated that way, and that is just equivalent to the differential form of that one. And then you also have an electric field here, and the differential form is here. You have an electric field. The integral expression of the electric field has two equivalent um, differential forms. This is just the Gauss law, and of course the curl of the electric field is always zero. And here we saw in this just a while ago that electric field is just the negative gradient of the potential, and this is just the integral form of that, and we have talked about that earlier on. So we're now going to look at electrostatic boundary condition. Now, when electric field passes through some boundary, when the electric field passes through here, for example in this figure, you have an electric field from below, and this is an electric field from below here, and it passes through some surface, which is this surface here. And this is not an ordinary surface, because this surface has a charge distribution sigma. And when it has a charge distribution sigma, the electric field down here comes out above, but it's not anymore the same value as it was when it was still not passing, or when it was still below the charge distribution. So how do we get the value or the difference between this electric field below and electric field above? So let's again use the Gauss law, because we have a surface here. So here we can see that you have a rectangular pillbox here with an area A, and then with an, of course, that's the thickness of this Gaussian pillbox is epsilon. And when you talk about boundary condition, you let this epsilon go to 0, so that the surface would be just the boundary. So that the Gaussian surface will just lie at the boundary, and then you can get the discontinuity of the two electric fields, the electric field below and the electric field above. So let's see. So using the Gauss law, the Q enclosed here, the Q enclosed is equal to sigma A. That's the charge. Actually, the charge is actually equal to, sigma, I mean, is equal to Q, the total Q, over area. So that the charge enclosed, or the charge in over the total area, I mean, sorry, so this is A, this is equal to Q enclosed over area. so that your Q enclosed will be sigma times A. So if A varies from point to point on the surface on or the surface is curved, then we have to uh, pick A to be extremely small, the A here to be extremely small, and the epsilon also to be extremely small. I mean, we have to let epsilon also to go to a limit that is very small. So, what is the electric field above? So by Gauss law, um, the electric field here would just be dA integral equal to 1 or sigma A over epsilon sub O. And this one you have E so anyway, the electric field that comes out here, the E here would be E above minus E below, so that this is of course constant. You can take that out of the integral. If you integrate dA, that would be A, so A will cancel here and the A here will cancel, so that you will have this expression. By the way, the side of the box will contribute nothing. The side of the box here will contribute nothing because of course the epsilon, you have to go to 0, so that this will become really small. This one here will, the thickness will become really small because you have to make your electric field perpendicular to the surface. That's why you have to make this area very small, and then in order to really get the discontinuity at the surface, then you have to let this epsilon approach to 0. So this one so you have now this is now the discontinuity of the electric field when it passes through a surface charge density. So this one now is a very important result, or an important boundary condition. So this is now a boundary condition BC, where E perpendicular above denotes the component of E that is perpendicular to the surface immediately above, and E perpendicular below is the electric field just below the surface. So we let the upward direction to be positive. So in that case, well, of course you can use the direction below, but the answer will just be the same. The direction will just be reversed, but the magnitude would just be the same. So, conclusion. The normal component of the electric field is discontinuous by an amount sigma over epsilon sub O at any boundary, in particular where there is no surface charge. The electric field is continuous. So if the electric field passes through a surface without electric charge, So the sigma there would be 0. So the electric field in that case would be continuous. The tangential component of E is always continuous. We talked about the perpendicular. Now the tangential component of E is always continuous. So why is that? You have here two components of E. Let's check that. Let's go back to the figure. Let's go back to the figure here. Wait. So here, let's draw an electric field somewhere in the pillbox. So let's draw an electric field here. So it has an E perpendicular. This is the electric field, and a tangential electric field. Yeah. So if you calculate that, the tangential electric field will just be, if you do this, looking at the if you do this for the tangential, wait, so you close the surface on the sides of the, because the tangential component of the electric field will come out of the side surfaces of the rectangle. So this one, you have to integrate the E dot dl by closed integral. Of course, that is equal to 0. And the electric field here, you're actually talking about the electric field that comes out of the sides of the pillbox. But the side of the pillbox will look like this. This one here. So what happens? So EL above, so if epsilon goes to 0, the side, the EL above would be the EL above times EL, E below times L, and the E above times L would be in opposite direction. They would be in opposite direction. The E below, because the electric field, the path here is going in this direction. The path is going in this direction, and your electric field is going in this direction for the line below, or for the line segment below, and for the line segment above, your path is going in this direction, and your electric field is also going in this direction. So that's positive. So what happens is that this one, E above times L minus E below times L is equal to 0. So L, you can cancel the L because it's a rectangle. The L are the same. So E above tangential is equal to E below tangential. So you have this one. So if you take the tangential and the perpendicular components of the electric field, you will be able to get this in general. This is the boundary condition for the electric field in general, talking about the perpendicular and take combining the perpendicular and tangential components of the electric field. So how about the potential? This is the potential. This is the potential here. So how about the potential above and potential below? What is the boundary condition there? So we'll take a look at this. So you have points A and B. You have a point below the surface A and a point above the surface B. So you can get the potential difference of the 2 points and do it like this. So the potential difference above and below is just V above minus V below, and so you have this. But what is the integral? What is the difference here? Because you're in the boundary to get to the surface. To get to the surface of the charge distribution, you have to let B close to the surface and let A close to the surface. That means when they get close to the surface, they approach to a certain value that they are equal. So that's why the A and B, if you let the path shrink so that they stay at the surface charge distribution, then if the limits are equal, then this is equal to 0. This is equal to 0, so that your V above is equal to V below. So that's the electric potential boundary condition on a charged surface. So we'll so anyway, this is the gradient of V. This electric field is a gradient of V, so you can rewrite that into this one. You can write that into that one, or this one is more appropriate because the direction of the electric field is just normal to the surface. So you can just, because the del here would just be, you can simplify the del because it's not anymore three-dimensional. It's just on the normal of the surface. The direction involved is on the normal of the surface. So you can simplify this one into this one here. So now let's continue. Of course, your partial of V with respect to n will just be that one, just the normal to the surface derivative. So only one component of this that is normal to the surface. For example, in Cartesian coordinates, if the x-axis is normal to the surface, then this n would be x, or if in Cartesian coordinates, I mean in cylindrical coordinates, of course r is always normal to the surface of the cylinder, and then for a sphere r is also normal to the surface, so it would be r. So n would just be the normal direction. So these boundary conditions relate the fields and potentials just above and just below the surface. Those are very important. Okay, so you can, if you have some free time, you can solve this problem. You can screenshot that, and then we're going to discuss in the next meeting or in the next session work and energy, because we don't have so much time for this. We are almost 1 hour, so I'll be putting out assessment for this lecture, and I hopefully you'll be able to finish it in the next week. The assessment for the previous lecture would be together with this one. So see you guys, see you class in the next meeting. So I have to end this recording now.